Okay, I want to check if it's recording first. Okay, I am going to do a presentation on Newton-Raphson method. So Newton-Raphson method is a method usually used for root finding. Okay, so some functions, we cannot solve them using analytical method like factorization, using the quadratic equation and so on. So such equations, we usually solve them numerically using this type of method. But usually we can start with something that is solvable, then check if the solution is possible. Okay, in this section, you'll study a technique for approximating the real zeros of a functions. The technique is called Newton-Raphson method, and it uses tangent lines to approximate the graph of the function near its x-intercept. This is a keyword. Yeah? So this is what I'm going to discuss on the summary. They say near its x-intercepts. Okay. Now, you heard that they are using the tangent lines. Okay, you can clearly see that you can start at any point here. This point x, let's start at the top one. At this point, xn and f at xn, here we have a tangent line. This is a tangent line. Okay. So we can clearly see that we plot this tangent line, and where it meets the x-axis, can you see here? Then we take another point. This point, it will be x at n plus 1. So we take another point here, we plot another tangent line at that point, and then where it meets the x-axis, we plot another. Here we take another tangent line. We see if I were to take another tangent line here, it will be close to the x-intercept here. So taking those tangent lines until you reach a solution, that's basically what we do with Newton-Raphson method. Okay. Now I'm going to derive the equation that we are going to use. So when I'm saying derive, you must show all the steps. I don't know, maybe I can do it here. I'll try to fit it here because I'll be using this graph here. Okay, now we know that the gradient m is equals to tan theta equals to y2 minus y1 equals to x2 minus x1. So this is the equation that will help us to get the equation that we'll use for Newton-Raphson method. Now I'm going to use the terminology that we have here. I'm not going to use y2 and y1. Now let's look at this point here. You see this point here. Let me change the color. So these are the points that we are going to use. You see this triangle. So we have a triangle here. This is the triangle I'm going to use to determine the slope. Okay. Now we have this point xn and that one. Okay, let's see. So we can write that this is equals to my y2. I must choose my y2 and y1. Okay. So let's say this is my x1 here, and this is my x2, and then here I have my y1. Then my y2 will be at this point here. So now let's see how I write that. I have my y1 is f xn, and then my y2 can clearly see that this is on the x-axis, so it will be 0 minus 0 all over. Now it's going to be xn minus x at n plus 1 here. Now I have everything that I want. But now the tangent line, M actually represents the derivative at a given point. So now the derivative at xn gives us our gradient. So here we have f prime xn. Okay, now from here we can end up with our formula. Now let's say write xn minus xn plus 1 is equals to f xn over f prime xn. I didn't do anything, I just cross multiplied. Okay, I didn't do anything new that you don't know, you just cross multiply. So cross multiply here, then you'll end up with this equation. Okay, now we want to make this guy the subject of the formula xn plus 1. So this means we have minus xn plus f xn over f prime xn, and multiply everything by negative. We have xn plus 1 is equals to xn minus f xn over f prime at xn. Now we are done. This is the formula that we are going to use for Newton-Raphson method. So you can see that we didn't invent the formula, we actually derive it step by step. So we are going to use this formula to determine our solution using Newton-Raphson method. Okay, now I'm going to move to the next page. Okay, so usually in my problems, I don't ask you to derive the solution. I want you to use this the final solution that I have here, this formula here, the final formula. You must be able to use it. Okay, so this space here was reserved for derivative derivings. Okay, now they say use Newton-Raphson method to determine the root of equation tan x equals to x with the initial guess x0 equals to 4.6. Round your answer to 4 decimal places. So here, always write your solution in this form. Your function fx is equals to. Now here you can choose. It doesn't matter. You can take fx to this side, or you can take tan x to that side. So I'll check in my solutions which one I have done. At the end, you'll arrive at the same solution. So it doesn't matter which one you use. Okay. Okay, let's say we have x minus tan x. And one student can, or you can use fx equals to tan x minus x. It doesn't matter. Any one of them must work. Okay. Now, what I have done is this. We have a table here. For those students who used old calculators, you can use this table approach. Okay. Now, it will depend which value they have given you. Here they have given me x0. It means now I'll start at 0 here in that case. And my n is 0, 1, 2, 3, and 4. So in some exercises, they start with n equals to 1. So it doesn't matter, it's just an order. Okay. Now, what I want to do now, I already have solutions for this one. Okay, so here is x0. It's a given value, it's 4.6. Okay, it's given. Okay, now you substitute this 4.6 in f of x, this f of x here, and write your solution. So let's check which one I have used. So 4.6 minus tan 4.6. And remember, in this case, you are working in radians. Okay, so let me start again. Tan x alpha x minus alpha x. Then if I substitute 4.6, what do I get? Okay, I made a mistake. I'll start again. I have a solution. I just want to, okay, then calculate 4.6. Okay, let's see what I have there. So if I were to change the order, okay, I'll explain the concept. I'm just checking it. Okay, it's okay. So in my solution, I have used this equation here. So you can use anyone, like I said. So that will be my solution. So I substitute 4.6 in, I'll just write the equation here. Fx equals to, let's see which one I choose. It's the one with x. X minus tan x, and your solution will be minus 4.26017. And remember, we are using radians. So if you use degrees, you'll be in trouble. Okay, now you differentiate this guy. F prime of x is equals to 1 minus sec squared x. Now you substitute on that one, substitute 4.6. So we substitute 4.6. Let's see. So if you're using the calculator, you can write it as 1 over cos squared x. Okay. So when I end up with minus 78.50270, and substituting into this ratio here or fraction, I end up with 0.05427. So you can check if I'm getting the same correct answers. So I'm substituting on this ratio, which is fx over f prime of x. So in this case, it's going to be x minus tan x over 1 minus sec squared x. So you are substituting here, you end up with this value. Now xn, so we have the formula that we have derived there on top, xn minus fxn all over f prime of xn. Substituting into this one, I get a new value, which is 5.4573. This is important. I'm doing it because I want you to see the pattern. So the answer that you have there becomes your x1, which is 4.54573. You start the process again, and then you end up with 4.50615. This becomes your x2. You continue in that fashion, 5.0615. So you continue in that fashion until you get your solution. Okay, now I'm going to look somewhere where I have done this to give you the whole solution. Yeah, the old one. Let's check this one. This is the old one. Yeah. So you'll end up with these values. I wanted to give you the whole answer. So this is what you'll end up with. And now you can conclude at the end that f, the root, what you are looking for, you're solving fx. The root x is approximately equals to 4.4934. Okay. So you can do this. Sometimes maybe you have the tuck shop calculator. This means you can still solve this problem. If you have those calculators, going step by step like this. Okay, now for those who have advanced calculators, So I've shown you that one. Now using a calculator here, I have a short video here. This video shows you how to use a Casio, this advanced one, Casio FX911Z Plus. So this and other one and the more advanced one, because they're improving every time. So this is the video that you're going to use, okay? Okay, you'll use that video. And now I'm going to solve the same problem that we have above there. You know the answer. Using Newton-Raphson method to determine the root of the equation tan x equals to x with initial value equals to x0 equals to 4.6, and then we have to round our answer to 4 decimal places. Now, I don't know if my calculator here will work. Casio. Okay. Can you see the calculator? Okay, can you see the calculator?
Yes, sir, it's on display.
Hello. It's on display. Okay, now what we are going to do is this now. Alpha, we are going to type the equation. Alpha x minus tan alpha. No. Okay, I see. I need to derive something first, okay? It's okay. Because that one I was doing step by step. In this case, let's say we are given fx is equals to x minus tan x. F prime of x is equals to 1 minus sec squared x. And then this means xn plus 1 is equals to xn minus what? We start with the function xn minus tan xn all over 1 minus sec squared xn. Okay. Now, this is what we are going to punch in the calculator, the equation on the right-hand side. Okay, let's do that. Okay. Okay, I have it somewhere here. Okay, so let's try to do that. We need this guy here. So it's alpha xn minus tan alpha xn. Let's try it again. Alpha xn, close the bracket. Okay, all over 1 minus. Now for sec squared, we have to be creative here. We'll write it as 1 over cos. No, this must be under division, sorry. Okay, 1 over cos, and then alpha x. Then we close that. And then we can square it here outside. Then square it. Yeah, let's change that. I forgot. So it's 4. It's in radians now, okay? Now you see here, after shift, we have what we call calc. On top of the solve there, you press calc, and then you substitute the initial value is for 4.6. So 4.6 equal sign. Okay, let's check. It's giving me a value I'm not expecting here. Why? I'm expecting 4.3. Let me see. Yeah, it's okay. I see my mistake. It's correct. Okay, I forgot the if you check on the formula, we have xn there, xn minus, that's part that I forgot to put there. So you see, you must engage your work and see where you have made a mistake. Yeah? So we have alpha x, okay, alpha x, okay, let's do it again. Alpha x minus. Now it's okay. It looks our formula is okay. Start with xn minus, that is correct. Now we say calc 4.6, which is there. I'm just typing it again, equals sign. Now this is the value that I'm expecting, 4.5457, okay? So that's our initial value that we have there. Now the advantage of using a calculator, once we have done this, now you can go to calc, then you say answer equals sign, calc, answer equals sign. You repeat like that until your successive answers are the same, okay, according to the requirement. You check the last 4 digits. If the last the 4 digits that you are looking for is the same, then you stop, okay? Now in this case, I can write the answer down. My answer here is, I'll write it what, because I started with x0. So my x1 is equals to 4.5457. Now I calculate again my x2. Let's see what this will be our x2. Now I'm going to say calc, I don't see it, I want to see it. Okay, the calculator is gone. Calculator, Casio. I don't know what happened. Okay, so we're going to start again. So you have a calculator in front of you. Now you have the initial answer is 5. I'm going to use my calculator here because this one is misbehaving. X minus tan, at least you know what is expected now. Alpha x, okay, all over 1 minus, here is, okay, then you repeat in that fashion until you have the solution. But I wanted to give you a solution. Cos alpha x, close this one, square. Okay. Okay, I have my first value. Now you press calc and then answer. Then your next answer will be, I have, this is equals to 4.5061. But usually, to be on the safe side, I think it will take 5 digits, okay? So calc 4.6, let's see the initial one. It was 5.4573 here, okay? Then you do calc answer equal sign. So I have this one. This is 5 here. Now x3, calc my answer equal sign. I have 4.49417. My x4, I say calc answer equal sign. This is equals to 4.9341. X5, calc answer. Now I have 4.9. No, I forgot the 4 here. 4.49341. Now you can see that my successive answers are the same. That's when I stop. Whenever you have this situation, you stop. Then you can say your x is approximately, the root that you are giving, we are looking for, is approximately equals to 4.4934. then you have answered the solution. So if you are using the calculator, you must write exactly as what I have done here. You determine your fx, you differentiate, you write your formula, then you can start using your calculator. This is the steps that I want. You get full marks by doing this. Exactly as what I have done here. Or you can use the table like I did here and arrive at that solution that we have. Still, we arrive at the same answer using those two methods, okay? So it will be up to you what method you choose, okay? Now we have activities here. The equation, we have 2x cubed plus x squared minus 1 equals to 0 has exactly one real root. Show that, now we are solving number 1. Show that for this equation, Newton-Raphson formula can be written as, now here basically what they are asking, I think this is wrong. What we are missing here, like I did in the previous one, we need x minus. Now let's do it step by step and see what you are going to get. And I was correcting these solutions today. I didn't see that. F is equals to 2x to the power 3 minus x squared minus 1. F prime of x is equals to 6x squared minus 2x. And now you rewrite the formula correctly. Xn plus 1 is equals to xn minus, now you at the top you write your fx, 2x to the power 3x. Don't forget the n, it shows that the function is changing. Those x's, they are not constant. All over 6x n squared plus 2xn. So this is the correct form. So I'll correct this one for the next class. So this is the correct form. So I wanted you to show that. So you can ask such questions. So this one will be a 2 marks question. Okay. Now they say use the formula given in part A with x equals to 1 to find the values for x2 and x3. Now you have to determine, you can see our n here. So they said, what is our xn? x1 is 1. So you can write this formula here if n is 1. So this will be 2 here equals to x1. I'm just trying to show you this 2x to the power 3x1 plus x squared 1 minus 1 all over 6x1 squared plus 2x1 to the power x1, just x1. Now you can substitute this x1 here, you get a value. Immediately after that, now you use your answer there. x3 will be equals to x2 minus 2x2 to the power 3 plus x squared 2 minus 1 all over 6x2 squared plus 2x2. So now let's just determine the way we have been doing. I'm going to use a calculator here just to determine those answers. So I have, so you'll have alpha x minus, then you have a fraction there, which is 2 alpha x to the power 3 plus alpha x squared minus 1, then you divide. I want to give you the answers there. I don't know if you have done it yourself. All over 6 alpha x squared plus 2 alpha x. Now you put calc, then you substitute 1. So my first solution that I'm getting here, I'm getting my x2 to be equals to 0.75. Now you use this 0.75 on the next answer. Calculate answer equals sign. I'm getting x3 is equals to 0. Did they give us the, they didn't give us the decimal form, so you'll choose here 0.0 6, 7. They didn't actually give us where we must end. Now, explain why for this equation the Newton-Raphson method cannot be used with x1 equals to 0. So please see that because of use of 0 and the fraction we need to solution. I find all this of x to the power 3 equals to x plus 6 correct 4 decimals using Newton-Raphson method. So here, basically what I wanted to illustrate is that sometimes they can give you a problem without giving the initial value. You see here, we don't have an initial value. So in such situation, I think the assessor or the examiner must give you a problem that is easy to plot. Okay, so you plot this graph here. Okay, and then once you have plotted this graph, then you can approximate the solution. We take a point close to this one. Let me show you. I'm going to plot this one. Okay, I'm going to plot it. So let's say here we plot. So that's what they were trying to explain. We plot. We need this guy here. E to the power 2x. Okay, no longer need this. Okay, x plus 6. Now let's see where we plot from. X comma from minus 6 to 6. Let's just. Okay, we can see that these two graphs, they will meet at approximately at 2. Okay. Okay, approximately at 2. Now let's take any value close to these two values, to 2, and then work out the problem and see what do we end up with. The problem is one, if we take a value that is far away from the x-intercept, it might be very difficult for us to determine the solution. Okay, let's see. Another thing. I want to see something. Another approach which we can use, but in a such situation for future research when you are using this method later. So if I solve for x here, what do I have? Those are my solutions. They look very difficult. Okay, let's just, use the graph. What do we here as a solution? Let's take a value close to 2 and see. A value close to 2. Let's say x0 equals to 1.8, and then you solve. So to solve this one, let's we have fx equals to e to the power 2x minus x plus 6. So this is equals to 0. Now it means that our f right here is equals to 2 e to the power 2x minus 1. So our solution here, we have xn plus 1 is equals to xn minus e to the power 2x plus 6 over 2e. Now we solve, and then in this case it's a trial and error. We have chosen 1.8. You might find that when you solve using 1.8, you don't the solution takes time to converge to a certain solution. It means that you have taken a value too far away from the x0. It is too far from your solution. So you must take solution. That's what you have to learn from this problem. It explains two things. You must choose a value close to the solution. Those are 1 mark question that will be asked. Why the solution of conversion? You explain solution conversion first of all. So that's what I wanted to explain here. Now see x1, what will be our x1? You can use the calculator. Let's use the calculator. Not like the calculator, wrong, which I do anyway. X to the power 2 alpha x minus x plus 6. And under the division sign, we have 2 shift, and then we have either 2 alpha x, okay, minus 1. I hope you have managed to type it. I've shown you. So calc, let's see 1.8 and see what you get. Hey, we're starting with minus 34. So you can clearly see that something will be wrong. This means this illustrates that our solution, if you look at our graph here, our solution here is close to 2. Here, they meet at 2. Okay. Now, if you look at this straight line, our solution actually will be close minus 6. So we can see that we are too far from the solution. The solution actually is there somewhere at minus 6. That's where we have the x-intercept. So now we need to take values close to minus 6. Okay. So we can stop there. Basically, that's what I wanted to explain with this type of problem. So for this module, you will be given the x, the initial value. Okay. So this one is beyond the scope. I just wanted to show you the case. Okay. Now the next one, they say find correct to 5 decimal places the x coordinate of the point. This one is similar. Okay, find the correct. Find correct to 5 decimal places the x coordinate of the point on the axis. So here the solution. Okay, I remember this problem. Okay, they say use Newton. So let's try to think about it. 5 decimal places the x coordinate of the point on the y equals the element which is the closest to origin. So I'll try to plot the rough sketch here to explain the concept. So I think this is an optimization problem if you look at it closely. Okay, so this will pass at 1. So this is the graph. So basically what they want here, yx, they want you to determine, you see here you can have, this is the graph. So you want a value, so you can check, it can be this one here. So we will use this distance formula actually to determine the value of x on this graph that is closest to the origin. So it's an optimization problem. Optimization problem. So I'm not going to solve it here. I can give you a solution later, but this is an optimization problem. Okay. Now, this is the summary. They say under summary here, I wanted to highlight 2 things before we end our class: convergency and using degrees and radians. So for this type of problem, I'll advise you to always use degrees. Now, when I was talking about convergency, this is the convergence. You see that as we calculate x1, x2, x3, x4, x5, at some point we end up with the solutions that are close to each other, or they're exactly equal. So it means here our solution has converged. Now, but if you come and look at this one that we're trying to solve, I took 1.8. My first solution was 34 point something. Okay, I will solve this problem. I can end up with more than 100 values. So in this case, you can see that it takes times to converge. Okay, I can end up with x 100 here in this type of problem because I took a value very far away from our x-intercept is minus 6. I took a value somewhere where next to 2. So you can see this is far. I'll calculate many values until I reach that point. Sometimes I'll even get bored and stop there. So convergence, for your solution to converge, you must take a value very close to your x-intercept, okay? And another thing, the main reason we use this type of method, you might find that the problem that we are solving, we are able to plot it, we are able to numerically. So we plot the graph, then we can see that no, the solution will be close here. Then we solve using the Newton-Raphson method. Okay. Now the other thing, you must always use radians, not degrees. With the degrees again, the degrees are so small compared to degrees, to radians. So using a very small numbers, your solution also will take time to converge if you use degrees. Actually, it's wrong to use degrees because you cannot mix. Remember, the radians are real numbers, basically. They are real numbers, the radians. So you cannot mix degrees and radians. And let's say, for example, here, let's do this problem. Here we assume x is here be real number. Okay, when you solve here, you must also use real numbers. That's the reason why we use radians. So that's very important. Students, most of the time, they know how to solve the problem, but the mistake that they usually make, they use degrees, and they lose all the marks. Or maybe lose 3 marks out of 5 because maybe they have presented the problem very well. Okay, so immediately after this lecture, now I'm going to introduce what we call binomial theorem. So if you have questions on this one, you can ask now before I start. Any questions under Newton-Raphson method? So I'll assume there's no question. You can still ask later on, even via WhatsApp, if you don't understand or you have a problem. So activities, you can check on the notes that I've sent to you via the chat in the previous classes. Okay, now let's go to the next topic. I said the next topic is binomial. Okay, we are still under application of differentiation. So here we are going to expand a given function using a binomial theorem. So sometimes you might find that it's very complicated to solve certain problems directly, especially maybe when you want to integrate. So you can use the Maclaurin series or binomial series to find an approximate solution of that problem. And another thing with the binomial, it is used in a situation like, for instance, for lotto and cell phones. Cell phone numbers. You can see we have only how many numbers? 10 numbers, 0 to 9. But from 0 to 9, we can have many cell phone numbers. So basically what they are using here, they are using the binomial series to determine that. Okay. And even load, so the same thing, we have about 45 numbers. So you can also calculate the chance of winning the load. So using binomial theorem, which is more than 1 in 14 million. So the chance is 1 in 14 million. So It's because a lot of application and in statistics also they use this binomial. I forgot they use this binomial series. Okay, and later last day we'll be using this. I'll think about it when you think about when you are busy working on this. Okay, now here I'll start with something that we know. To expand here, you know that you have A plus B and A plus B, and this is equals to A squared plus 2AB plus B squared. Okay, so this is how I multiply it. Okay. Now, for this one, we use our previous answer, A plus B squared multiplied by A plus B. So we have A squared plus 2AB plus B squared multiplied by A plus B. So here we end up with 3 A to the power 3 plus, I'm multiplying everything by A, so it's going to be 2A squared B plus AB squared plus, now multiply everything by B, so it's going to be AB A squared B plus 2AB squared plus B cubed. Now, simplifying this, I have A to the power 3 plus 3A squared B plus 3AB squared plus B cubed. Okay, similarly with this one, we do that. So this will be equals to A plus B to the power 3, A plus B. So the previous answer is multiplied by that. Let's say A to the power 3 plus 3AB squared, A squared, plus 3AB squared plus B to the power 3. We multiply by A plus B. So here we just expand this one. So we have A to the power 4 plus 3A cubed B plus 3 squared B to the power B. Let me see how I do this. It's A squared, B squared, yeah, B squared plus B to the power 4. Not B to the power 4 plus, my mistake here. I'm still multiplying by A. So this is A here, B to the power 3. Now plus, now multiplying by B is A to the power 3, B plus 3 A squared B squared plus 3 okay, let's see. Yeah, multiply by B is going to be 3A B to the power 3 plus B to the power 4. Now simplifying this, taking the like terms of A to the power 4, now you can see this like term, this should be plus 4A to the power 4 plus B, another like terms plus 6A squared B squared, adding this, another like this one's going to be 4A B to the power 3 plus B. But Hello, are you still there? Are you still there? Hello, Bushu, can you hear me? I can see my recording will be bad because it's stopping and starting, okay? It's a bad network. So I don't know, should I continue or stop here? Should I stop the class or continue lecturing?
So I think it would be best if we stop the lesson for now because you've been breaking for about 20 minutes ever since the class has started. So if you may share the slide for today, I think that might work.
Yeah, let me share the slide and stop. I think I have to lecture at school next time. I'll share both of the two slides. Let's start with Newton-Raphson method. Okay, I've shared the two slides. So I'll meet you in the next class. Okay. Which is Monday this time. I thought Monday I'm going to lecture next week. So we'll meet Monday.